right, so now let's fast forward up to more modern times. So the modern era of geometry really begins in the 17th century, as so much of mathematics does. In this case, with the work of Descartes and Fermat, who introduced Cartesian coordinates. And this is something you'll all be familiar with, the power of x, y plane and a sheet of graph paper to be able to precisely say what's going on. So there's a completely new way of thinking that allowed the 17th century people to really get a grip on geometry in a way that the ancient Greeks were not able to. So we have very precise ways of specifying points. And we have very precise ways of specifying vectors. So a vector, for example, this vector from A to C, it's a directed line segment obtained by taking the differences between the points, these endpoints. So it's the vector 6, 2, meaning we're going over 6 and up 2. And so we make these nice computations. So we have vectors and points, and this vector is the same as that vector. But not only do we have points and vectors, we also have lines. So lines become linear equations that you're all familiar with, either this in this form or maybe this form. So there's some two lines with two equations, and we can, for example, calculate a meet. And collinearity of points, well, that also becomes a very nice kind of issue in this kind of framework. We have 3 points. We want to know whether they're collinear. Well, maybe they look collinear, maybe not. So we create the vectors. There's the vector 3, 1. There's the vector 5, 2. We want to know, are these vectors parallel? Well, to determine parallelism, it's if one's a multiple of the other, then this times this equals this times this. Or this times this minus this times this should equal 0. And since this times this minus this times this is not equal to 0, they're not collinear. And that's closely connected to a lovely formula for the area of a triangle. So here is a triangle in the Cartesian plane with A here, B here, D here, C here. So this is the vector AB. This is the vector CD. And then if we want to know what the area of this triangle is, well, we can make a lovely little calculation because it's the area of the big rectangle, which is AD, minus these 3 triangular areas, which are easily calculated. That one's AB over 2, that's CD over 2, and that's A minus C times D minus B over 2. And we work that out, we get AD minus BC over 2. And so this same kind of expression occurs, that AD minus BC over 2 is the determinate form for the area of this triangle. And this is a linear algebra expression. We say that the determinant of this 2 by 2 matrix is this expression. So it's a very important quantity associated to a 2 by 2 matrix or this triangle. And again, it's a sort of a link between the algebra and the geometry. Okay, I want to show you now, go back to some projective geometry, which is a very beautiful subject, which is unfortunately not taught these days. It really ought to be taught in high schools. In fact, in primary schools. It's such a beautiful subject, has such a great history, and it's really the foundation for so many things. And it's such a simple subject in some ways. So here is the first theorem in projective geometry, both historically and really in terms of logical importance. It's Pappus's theorem. Pappus lived around, Pappus lived around 300 AD or so. And the statement is you have 2 lines, 3 points on the first line, 3 points on the second line, and then you join the A1, the A2 and the B1 point and the A1 and B2 point, and you get a point of intersection, call it X. You join the A2 and the C1 and the A1 and the C2, you get another intersection point called Y, and then you join the B2 with the C1 and the B1 with the C2, you get another point Z. And then Pappus's theorem is that these 3 points, X, Y, and Z, are always collinear. This is a theorem that doesn't involve any distance or angular measurements. It's a theorem of projective geometry. And then you can tell your students about the most important and famous theorem discovered by a teenager. Okay? That was discovered by Blaise Pascal, a brilliant French sort of genius, an all-around interesting fellow. Who in 1640 discovered a generalization of Pappus's theorem, which is that if you have a conic, like an ellipse, or a hyperbola, or a parabola, then you have 3 points and 3 points, then you do exactly the same thing, and the 3 points x, y, and z are still collinear. It's a generalization of it. This is actually of considerable practical and theoretical importance. GeoGebra, you will know, perhaps has a capability, if you have 5 points, determine typically a conic. And you might want to know, well, how does GeoGebra calculate that conic for given 5 points? Basically, GeoGebra will use behind the scenes, under the bonnet, this theorem. Because this theorem, roughly speaking, says that if you know these 5 points, then you can create enough lines to figure out this other point if you have some other piece of data. Like if you know this line through that point there, then you can create that 6th point using this fact. And so projective geometry is not just about collinearity, it's also about perspective. And it arose in the modern times, perhaps through Renaissance artists' attempt at trying to figure out how we take a 3-dimensional situation and portray it accurately in 2 dimensions in a picture. So for example, let's say you want to show your students what the curve y equals x squared looks like. But I mean like really looks like. Okay. Of course, we all know that usually we draw y-axis, and then we draw y equals x squared. That looks like that, right? We've all done that hundreds of times. That's not really the true picture, because that's only just sort of part of it. Okay. What you want to do, perhaps, is you want to think of the xy plane as a huge plane on which we are standing. Okay, so imagine there being no buildings. We're just on an infinite plane, and there's an x-axis in front of us, and there's a y-axis running off like this. And we have a button, we can press y equals x squared. And then the curve y equals x squared lights up. We have our mobile phone, we want to take a picture of it. We're going to take a picture of it. What are we going to see? Well, as we look out to the horizon, there's a horizon. That's up here. That's the horizon. So we're standing here behind the x-axis, so we're looking out. Here are these various grid lines. That's x equals 1, x equals 2, x equals 3. These lines are all parallel, so when we look at them in perspective, in real life, they will be like railroad tracks. They will converge to a point at on the horizon. If you actually looked at them, that's what you would see. The parallelism is only if you kind of look at them like this. Look at them like this. And then it turns out that y equals x squared looks like this. So there's the point 1, 1. There's the point 2, 4. There's the point 3, 9. There's the point 4, 16. And it kind of wraps around to touch the line at infinity. It's a real picture of the parabola. It's a great picture to show your students. How do we draw a picture like this? The Renaissance artists realized it's not at all trivial making a good picture like this. How do you know how to space these things out in the right way? You can't just do it arbitrarily. They realized that the key to making a successful picture like this is to look at diagonals. Okay? The key fact is that a diagonal like this, or like this, or like this are also parallel in the usual sense, so they will also meet at a point of infinity. So it's having that other point at infinity that allows you, say, if you just start with that as your initial configuration, and this is a great exercise, you can, with GeoGebra, you can, just knowing this is the original configuration and where the horizon is, you can then reconstruct the entire picture, just with lines, with a straight edge. Okay. But geometry is more than just collinearity and lines. So there's also perpendicularity, one of the very important concepts. And perpendicularity, of course, is also expressed very pleasantly algebraically. Two vectors, vector 3, 1 and vector minus 1, 3 are perpendicular. There's 2 perpendicular lines. And that's the basic expression for perpendicularity algebraically is just this one, that the vector AB is perpendicular to the vector minus BA. That's the basic rule that allows you to get control of perpendicularity. Okay, so once you have this perpendicularity, then you have metrical structure. And then we can talk about the second degree curves, which are one step up from the lines. And these are, of course, conic sections, going back to Apollonius of Perga. who studied conics, really as conic sections. So this is a cone, two-sided cone, and Apollonius realized that if you slice this cone with a plane, then you get a conic section, like an ellipse here, or a hyperbola if you slice it like this, or if you slice it exactly in the right way so that the slicing plane is sort of parallel to one of the lines in the cone, then you get a parabola. Okay. So this was well known, but remarkably, Descartes realized that with his algebraic coordinate system, these conic sections of Apollonius could be reconfigured. They really ended up being just the second degree curves. So you go up one step from linear. Any linear equation in x and y is a line. So you write down some arbitrary second degree equation, so with x squared term, xy, y squared, x, y, and some constant, and then that will always be a conic. It'll be one of Apollonius's conics. So for example, there's some examples, and there's the corresponding conics. Of course, it's a bit of technology and understanding required to unravel which one is which and how do you, in general, tell, and so on and so forth. Okay, I want to talk about another very important understanding of the ancient Greeks that that students really ought to know about. Okay, this is the rational parametrization of the unit circle, which is one of my favorite topics for undergraduates. So the unit circle x squared plus y squared equals 1. You'll all know that it has a parametrization as cos theta sine theta in terms of the circular functions. I'm not a big fan of these circular functions, I have to be honest with you, because yes, you can get your calculator to spit out approximate values, but you can't actually get at points completely accurately with this kind of transcendental function. But remarkably, Euclid knew a rational parametrization, which is this one here. It's a fabulous formula. Okay? So what is this formula? It's saying that, so there's an x-coordinate is 1 minus t squared over 1 plus t squared, and the y-coordinate is 2t over 1 plus t squared. Okay, so what we're saying is that actually here's the geometry, that if you take a point t on this axis, and then you draw this line here, and you see where it intersects the circle, it turns out that this point has exactly these coordinates. Yes?
For all the rational points that I went from that formula, what you're actually generating also is Pythagorean triples.
Exactly, that's exactly right.
That's what I talked about this morning.
Oh, you did? Okay, I didn't come to your talk. Okay, so, yeah, that's exactly right. So hidden in this formula are Pythagorean triples, because if you take 2t and you take 1 minus t squared and you take 1 plus t squared, those three numbers form a Pythagorean triple. That's right. And it's also closely related to what's called sometimes a Weierstrass substitution or half-angle, tan half-angle substitution in calculus. There's a certain kind of trick that you play in calculus that crucially involves really this formula. But in any case, it's something that students should know, and well, and this is just an example of different kinds of explicit example. Well, sorry, come back. This is an example. Like, for example, if t is equal to 0.2, then this is the number 12 over 13, 5 over 13. There's the Pythagorean triple, 5, 12, 13. And if t is 0.3, then you get 91, 109, 60. Maybe a less well-known Pythagorean triple, and so on. Okay, this diagram, for some reason, doesn't come out very well, but it's another very, very beautiful and important discovery of Apollonius again, going back 200 BC. That it's really one of the most remarkable properties of a conic. So if you have a conic in the plane, like this one here, then there is a correspondence then that ensues between points and lines. So this point here and this line here are in correspondence. Okay, and the correspondence is such that as this point, say, happens to move towards the the conic itself, this line will move correspondingly towards being a tangent. So when this actually becomes on the curve, then this corresponding line becomes a tangent. And you can move this point over here. If this point was over here, then the polar would be something like this. And as this the point moves further away, the polar would approach sort of a diameter. And now what is this correspondence? There's an absolutely incredible fact here. So if you want your students to play around with GeoGebra, this is a great thing for students to actually play around with. It's actually a theorem. It's not some toy thing. It's really a powerful fundamental fact. Okay, so what you do is, so you have a point and you have a conic and you want to generate this line. How do you do it? You choose two lines through this point that meet the conic. In this case, say that line and that line. That generates these 4 points of intersection. So those 4 points have additional lines that meet in points. So if you draw the line through those 2 points and you draw the line through those 2 points, they will meet in a point. And if you draw the line through these 2 points and through these 2 points, they will meet in a point. And that's how you then generate the line. You then just choose the line that goes through those 2 intersections. But the remarkable thing is that this line does not depend on the 2 orange lines that we chose to go through our given point. If you change this line, move it over here a little bit, then these points will move around, but the blue position will not change. So there's this sort of God-given polarity defined by a conic, and it's really a lovely thing. Okay, so let me just mention a few other classical things that you've probably all familiar with that are nice things for students to explore. Classical geometry, very lovely. The centroid of a triangle, which is the intersection of the 3 medians, lines from the vertices to the midpoints of the opposite sides, meeting in the centroid. That's the point of balance of the triangle. The orthocenter, which is the meet of the 3 altitudes, lines perpendicular to the opposite sides. And over here, the circumcenter, which is the meet of the 3 perpendicular bisectors. So you take a side, and you take the midpoint, and you take a perpendicular through that midpoint. Perpendicular through the midpoint, perpendicular through the midpoint. They meet in the circumcenter, which is the center of the unique circle that passes through the 3 points. So these 3 points were, again, known to antiquity. They were known to the ancient Greeks. So there's a fact associated to each one of these, namely that these 3 lines are actually concurrent. These 3 lines are concurrent. These 3 lines are concurrent. This one is almost obvious. This one is not so obvious. This one is quite curious. Evidently, this was Einstein's favorite geometrical fact, that the 3 altitudes of a triangle meet in the orthocenter. It is a lovely fact. And then we fast forward up to the 18th century to the great towering genius of modern times, Leonhard Euler, who was far and away, in my opinion, the most dominant mathematician of modern times, who, amongst many other thousands of things that he discovered, one of the things he discovered was that if you actually look at these 3 points in an actual example, you find that they are all collinear. The orthocenter, the centroid, and the circumcenter are collinear, and moreover, they're always in the ratio of 1 to 2. This is called the Euler line. And actually halfway between O and G, there's another point called the 9-point center, which turns out to be the center of the beautiful circle that goes through the 3 midpoints, which it's called the 9-point circle because it has some additional points on it. So anyway, this is always a very rich topic. So if you have some students interested in geometry and you want to give them something interesting to do, have them explore this. It's a great thing. Okay, I might skip this for lack of time. I want to tell you a little bit about, all kinds of interesting things. I want to tell you a little bit about rational trigonometry, which is the topic of my book. And so what is rational trigonometry? So rational trigonometry is a rethinking of trigonometry. And I'm hoping that someday it will actually replace classical trigonometry in high schools. a very heretical idea. Okay. But it's actually considerably simpler than classical trigonometry. And once you understand rational trigonometry, you realize, classical trigonometry, you're really burdening students with a lot of stuff just to do relatively simple things, as it turns out. Okay. So here, let me try to illustrate that briefly. So here is a standard triangle. Let's say it has sides 4, 5, and 7. Okay. So in classical trigonometry, you are, for example, able to calculate the angles. That's deemed the important quantity. So you want to calculate these angles, and there's various laws, like these laws will be familiar: cosine law, sine law, sum of angles, and so on. So you can calculate these angles, but when you do, you get that they're numbers, so these some kind of numbers, and these numbers are not exactly correct because they're just approximations. They're actually infinite decimals that go on, have infinite amount of complexity in them. So classical trigonometry is necessarily a kind of an approximate subject that's really more an applied subject. It works, but it's not really that elegant theoretically. Okay, so in mathematics, these two triangles figure very prominently. This is a 1, 1, root 2 triangle, but it's labeled somewhat differently. You'll notice that there's no root 2 here. There's a 2 instead of a root 2. And instead of having 45 or pi by 4 there's a number half. And there's this number here. And here, this equilateral triangle, instead of having 60 degrees, there's 3/4. And there's a eighth. So there are these other quantities that become visible to you, called quadrants, spread, and then quadria. But I'll only tell you about quadrants and spread briefly. Okay, so what's really going on? So it actually also goes back to the ancient Greeks. If you have a Pythagorean right triangle, Pythagoras' theorem, so the way Euclid thought about Pythagoras' theorem was not the way that the textbooks these days explain Pythagoras' theorem. Very different. It's very, very illustrative to understand this. To Euclid, Pythagoras' theorem was a relation about the areas of 3 squares. So you had this side, so you build a square on that side. You have this side, you build a square. You build a square. And Euclid's formulation was that if this is a right triangle, then the area of this square plus the area of this square equals the area of this square. Okay. So crucially, that does not involve addressing the irrationality contained in the lengths of these sides. Right? If you wanted to calculate the length of this and then square it, at some point you have to create this square root, and that's really only given approximately with an infinite series. So hidden behind the Euclidean point of view is really this idea that this quantity here, the quadrants between 2 points, which is the square of the distance, is actually more fundamental. Okay? So in rational trigonometry, one forgets about distance and just focuses on quadrants. Says, okay, here's the definition of the quadrants between 2 points. And then Pythagoras' theorem becomes this linear relation that Q1 plus Q2 equals Q3. That's more really like Euclid did. Okay, what replaces angle? That's a little bit more crucial, a little bit more novel also. So if you have 2 vectors, V and W, okay, we're all used to the idea that, okay, there's an angle. The angle is between 0 and 180 or something, depending on which system you were measuring it. So in rational trigonometry, we want to measure the separation between lines in a different way. And what we do is we use this formula here. There's a number of different formulas, but this is the one that's convenient. So you have some vector, let's say the vector AB, another vector CD. Then the formula is you take AD minus BC squared. I remind you that AD minus BC was the area of that parallelogram. So we're taking the area of that parallelogram and squaring it, and then dividing it by the quadrants of the sides. Basically just taking an area, squaring it, and renormalizing it in a rational way. And we call that the spread between the 2 vectors. So now spread goes from 0 to 1. 30 degrees is a spread of 1/4. 45 degrees is a spread of a half. 60 degrees is a spread of 3/4. And then after you get to 1, then it goes back to 0. 3/4, 1/2, 0. 1/4, 0. Okay, so the same triangle that we started with, the 4, 5, 7 triangle, in rational trigonometry would look like the quadrants would be 16, 25, and 49. And then these spreads, not angles, but rather spreads, turn out to be precisely 384 over 100, 1,225, 24 over 25, and 24 over 29. So the infinite aspect of angles is removed, and the 3 laws of trigonometry, that the cosine law, the sine law, and the sum of angles formula, get replaced with these polynomial relations. These are polynomial replacements for those laws that you drill into your students. And I claim that there's a lot of evidence that this way of proceeding is actually much more efficient. Okay, so there's lots more to say, but I'm not going to say any more now. I'll just mention that there's lots of sort of theoretical advantages to thinking about things, but I think really the killer application is this, that in principle this is gives us the possibility of dramatically simplifying high school math education. It's not going to happen next year or the year after, but in a few decades it's possible that rational trigonometry might start to be seen as a viable alternative, and when it does, it will simplify the teaching of mathematics enormously. Enormously. My book is called Divine Proportions, Rational Trigonometry to Universal Geometry, and it's a free download at ResearchGate under Norman Wildberger, so you can just download it. But in fact, I have some copies over there, so I'm handing them out to you gentle people for having put up with me for an hour. I'd like to just finish by saying a few things about the University of New South Wales and some of the projects and things that I'm involved with Daniel Mansfield. So shortly, in 2 weeks, we are about to launch our Future Learn MOOC. So MOOC is a massive open online course. This is meant for sort of senior high school students. It's pre-calculus, maths for humans, linear, quadratic, and inverse relations. It's something you can sign up for at futurelearn.com. This is like a British equivalent of Coursera. You've probably heard of Coursera or EDX. These are platforms for teaching thousands of people online at the same time. So this is our venture into this initiative. And also I'd like to mention that the UNSW School of Mathematics and Statistics present open learning professional development courses. So we have currently 4 courses that have sort of been developed, and we're creating some more. So these courses are going to be running sort of every couple of months. The next one is Peter Brown's course. Maybe many of you will know Peter Brown. He's had a long involvement with high school and HSC things for many years at the University of New South Wales. He's our first-year director. So his course will be Primes, Modular Arithmetic, and RSA Encryption. And then Daniel's course, Population Growth and Logistic Curve, also Curves from Apollonius to Bézier, and Archimedes and the Law of the Lever. These are amongst the courses that we're putting together. And so you can have a look at, for example, on the School of Maths web page, there's a high school section. And if you look under professional development, you will find these. We also have a little desk out there with all the textbooks and so on. So please drop by and say hello and get a little bit more information from us. And finally, we're into YouTube kind of thing. So School of Maths and Statistics has a YouTube channel. There's the user. So we have now more than 300 videos on calculus, linear algebra, discrete math. These are aimed at our students, but they are resources that we're creating for our students so that they can have examples of problems that are to solve. And here's my own YouTube channel. I've been doing this for a while. I have more than 500 videos and lots of subscribers and views. And I have series on various things. But for maths high school teachers, I would maybe think that maybe this one is of interest, right? So this is a course in the history of mathematics, where I go through quite a lot of the history of mathematics, and it's a really good thing, I think, for high school teachers to, it somehow gives them a way of putting a lot of mathematics into context. So have a look if you're interested. That's at Insights into Mathematics. The username is NJ Wildberg on YouTube. So thanks a lot for your attention, and if you feel like it, pick up a book.
Because at your desk table, you've got Parabola magazine.
Oh, we have Parabola magazine. Yes, you can pick up some copies of that, and we have various other pamphlets and so on. So thanks.